Hello everyone, welcome to the 16th session of Electromagnetic Theory and Interference course. We are studying about electrostatics in this particular module. We are going to see about the relationship about the electric field intensity and electric potential through which we will obtain the Maxwell second equation, and we will solve a problem based on this concept. Okay. So we already know from the previous session that potential difference between the 2 points A and B, okay, it is going to be independent of the path taken. So VBA is equal to minus VAB. So how can I rewrite? So VAB, if I take the left hand side, it is going to VBA plus VAB is equal to 0 actually. And I can relate it to electric field intensity by closed line integral of E dot dl. So E dot dl is equal to 0. What is the inference here? The line integral of E along the closed path, okay, it is going to be 0. Why the line integral is 0? Because there is no net work done in moving a charge, okay, along closed path in the presence of electrostatic field. Since there is no net work done, it is going to be 0. And now we are going to apply the Stokes theorem, whereby we will arrive the Maxwell second equation. So let us see the Stokes theorem here. Stokes theorem states that the circulation of a vector field around a closed path, okay, L, closed path, circulation of the vector field is equal to surface integral of the curl of the same vector over the open surface area. So it's going to relate my line integral of the vector field, the surface integral of the curl of the same vector. So we are going to just replace this E dot dl by del cross E, that is curl of the vector over the open surface. So this is also going to be 0. So we can write that curl of the vector field is 0. So if the curl of the vector field is 0, we already know it is irrotational vector, and we can call it as this vector field as conservative field, okay, because this line integral does not depend on the path of the integration, right? And here this is my second Maxwell equation, del cross E is equal to 0. This is valid for static electric fields. Okay, we are studying about the static electric fields only in this module, and this is the differential form and this is the integral form of the same equation. Okay, now let us continue our relationship, finding the relationship between the electric field intensity and electric potential. We already know the potential is equal to negative of the line integral of E dot dl. Okay, we already know what is E vector and what is dl vector in Cartesian coordinates. Okay, and we are going to find the differential potential dV. For that, if I have to remove the, if I take the differential, then integral goes off minus E dot dl. If I dot product these two vectors, I will get, already negative sign is there, I will get Ex dx, okay, along with the negative sign minus Ey dy, Ez ds. Why? Because my dot product of same unit vectors will turns out to be 1. Only that terms will retain. Other terms will get cancelled because dot product of different unit vectors are 0, right? So from the calculus of multivariables, the total change, okay, dV is going to be the sum of the partial changes with respect to x, y, and z. So I can write dV in terms of dou v by dou x into dx plus dou v by dou y into dy plus dou v by dou z into dz. So if I relate these two expressions, I can find Ex is equal to minus dou v by dou x, similarly Ey and Ez. And now I am going to substitute all the values in this E vector. If I substitute, I will get minus common out dou v by dou x into x cap plus dou v by dou y into a by cap plus dou v by dou z into az cap. We already know this partial differentiation, okay, differential vector component is del v. So E is going to be minus del v. This is our relation. So see here, electric field intensity is going to be the gradient of V. Why the negative signs comes? Because the direction of electric field intensity is opposite to the direction in which my electric potential is increasing. Okay, and if I want, now let us substitute the relation between E and V in our Maxwell second equation, that is del cross E is equal to 0. If I substitute the E value here, what I will get? Del cross del V is equal to 0. I have neglected the negative sign. So what does this equation tells us? So it implies that E electric field intensity must be a gradient of some scalar quantity only, because curl of a gradient of a scalar function only, it is always 0. We know this property. Based on that, electric field intensity must be a gradient of some scalar function. That scalar function is here is electric potential. Uh, so we have found another way of finding the electric field intensity apart from using the Coulomb's law or Gauss's law in this session. Let us apply the same for doing this problem. So a potential is given, okay, and we are asked to find the electric flux density d vector at this particular coordinate, and also they are asked to compute the work done in moving a charge from point A to B. By seeing the first part, okay, electric flux density, we know the relation between D and E, epsilon on T. And just now we saw the relation between E and V. So E is equal to minus del V, right? And seeing the coordinates and this expression, we can see that it is having the spherical coordinates function, r, theta, and phi. So we have to write the gradient function in terms of spherical coordinates. So that is going to be negative is common, dou v by dou r into ar cap plus dou v by r dou theta into a theta cap plus dou v by r sin theta d dou phi into a phi cap. So here, if you differentiate partially this expression with respect to r, what it is comes, it is turns out to be minus 2 by 1 by r square. Partial differentiation is minus 2 by r cube. So minus 2 and this minus get cancelled and the 10 got multiplied. So 20 by r cube. Rest of the terms are constant. It is there. Into ar vector we have to write. Then 1 by r is we have to multiply here. So 1 by r cube will be there, and minus and into 10 is minus 10. Now we are going to partially differentiate with respect to theta. In the differentiation of sine theta is cos theta. So cos phi remains same, a theta cap. And for the next term here, okay, what happens? Sine theta 1 by r sine theta, in that it get multiplied with and comes r cube in the denominator. Sine theta and sine theta get cancelled. Cos phi differentiation is minus sine phi. Minus sine phi, and along with this negative common outside will turns out to be plus, and this 10 get multiplied. 10 by r cube sine phi a phi cap. So we are now going to substitute in this expression. Epsilon naught, we already know the formula. Okay, 8.854 into 10 power minus 12. Okay, we will substitute in this permittivity of free space constant, and we are going to replace this r by 2, okay, and theta by pi by 2 and phi by 0. So while doing that, what happens? Sine 90 is 1, cos 0 is 1. So this 20 by r cube is r is 2, right? 2 cube is 8. 20 by 8 ar cap will come. For this cos 90 is 0. So this entire term get vanished. Here sine 0. So see sine phi, sine 0 is 0. So entire terms get vanished. So we are left with the constant along the direction of ar cap only. So the final answer is represented in terms of pico coulomb per meter square. Now let us find the work done. Okay, work done, we already know the relation. It is a force into distance, and if I substitute for force Q into E, okay, we can find a work done by uh, multiplying the charge and the potential difference. Okay, VB minus VA. We are going to just substitute the value. Q we already given 10 microcoulomb. Substitute 10 into 10 power minus 6 and substitute these point VB first. Okay, we have to substitute in this given expression B for R, theta and phi for at B and A. We will arrive this answer in microjoules. I hope you enjoyed the module 1 of electrostatics. Thank you everyone. Let us meet in the next module of magnetostatics.